So when we decided a few years ago to work on biodiversity, we had some problems to understand how from space, you know, at 800, 700 kilometers high, how can you look at species, at genes? But when you look at the Convention on Biodiversity, you realize that actually it goes from genes to ecosystems. So when we talk about ecosystems, there is a place for the European Space Agency. Since I guess that some of you, or most of you, don't know very much who we are, what is the European Space Agency, I wanted to include a few slides. It's quite important as well when you will talk to your students that you explain how the space policy is structured in Europe. So the European Space Agency has more than now 40 years of existence, and the second article of the convention always remained the same from the first day. So what is very important here, apart from the fact that we have to do space research and technology and develop space applications, that's very important, we are still in a context of exclusively peaceful purposes, even if this might change in the coming years. In terms of member states of the European Space Agency, you see that in contradiction with the European Union, we don't have any whole. We have no, it's not, let's say, talking about biodiversity, I would say it's not fragmented. And so we have 11 member states, the last one is Romania, but we have cooperating states, mainly from, should be one of these, no? Yes, mainly from the eastern part of Europe. That means that this country, Hungary, Poland, Slovenia, Estonia, Latvia, they will very soon be part of the European Space Agency. So big agency, high number of countries involved, difficult to make an agreement. That's always the key message we have to pass. So it's exactly the same as for the international environmental conventions. Strategy, European space policy. This is not only, and this is also very important for you, this is not only a matter of the European Space Agency. It's a matter of the Europe as a whole. And when the space policy for Europe has been defined, it was done, oh sorry, I wanted to show you, it has done with the ESA member states and the member states of the European Union. So it's a joint European space policies of all member states of two, let's say, of the European Commission and of the European space agencies. And a couple of objectives of that space policy is listed here. What is important, always I'm trying to really to bring you into biodiversity, is that we have to develop space application to serve public policies. And that's very important. Of course, the security is always a very important topic. The fact that we have to build in European independence, we have to contribute also to developing a European capacity is important, but space application responding to space policy is really a key issue. And in the line of this European space policy or strategy, we launched it about 10 years ago, and I think you have to know this, because this is very important for biodiversity. A very important initiative where, let's say, the Commission and the Space Agency and the National Space Agencies and whole, let's say, agencies dealing with environment and with security commonly agree to provide timely and reliable information that are policy relevant. Policy relevant means responding to policies at national level, but also responding and the obligations of the member states at international level. And this on the status and the evolution of the environment and also on the security of the citizens. I will not, it's the last time you see the word security here, I'm going now to talk about environment, but I mean, you see that environment has a very important place within the European space policy. So on one hand, you have the public policies on environment, and on the other side, you have all the observing systems going from ground, going, let's say, from laboratory instrumentation, going to field, up in the air with airborne sensors, and up to the satellite. So it's not only about satellite, it's about observations. So they have a need that are all policy driven, because there's a policy on biodiversity. So there's a need for information, and what we are trying with all these partners is to provide solutions to give this information in order to help the implementation of the public policy. Responsibilities, ESA is responsible. We are, let's say, a space agency. We build satellites, so we have the responsibility of the space part. Space component means the satellites, but also all the ground infrastructures. And, very important for you to know, the European Commission, with the member states, of course, must develop the service component. So anything at European level, it actually goes even larger than the European levels, that can help assessing biodiversity for Europe, will come, if it's not coming, of course, from the national, the member state, the national countries, will come from the EC. And for EC, biodiversity is a key issue. In ESA, we have, you see, a very long series of satellites, let's say, flying or ready to be launched. You have to realize that it took us almost 15 years to build these two, and in 15 years we are building the other ones. So you see, so we are going to have much and more satellites flying around the Earth and looking at different things. Some are relevant for biodiversity, some less. This one, yes, it's on the ocean salinity and the soil moisture. Soil moisture is very important. This one is looking at the gravimetry, which is important for ocean circulations. And this is an important topic for biodiversity. Cryosat, well, it's about the cryosphere. It was built mainly for ice sheet, but we also use now for other type of, let's say, parameters in the cryospheres, like the ice sheet. Then we have, this one is more on the wind field in the atmosphere. EarthCare is the electromagnetic waves, and so on. These are more scientific missions, so made for science, for Earth science. This set of satellites, this one is, ES1 is that now. It was launched in 91. In 95 we launched that one, and in 2005 this one. They are still flying these two. These are the future operational missions. Not all futures. Meteosat and METOP, these are meteorological satellites and are always, let's say, this is a series of Meteosat satellites. And then we have, and this is very important for biodiversity, a series which is funded actually by GMES, so by the Global Monitoring for Environment and Security, to look, it's what we call them, these are more scientific satellites and they are more operational satellites. Operations is that we take the commitment to provide data within this time frame with this quality, and this is serving the, as I said before, the public policies, but there is obviously a side use of the data for science as well, but it's really made for operation. And you have one embarking. I will come back on the radar and the optical instruments, because you might not be aware of the different sensors. So this one is mainly looking, let's say, principally at ocean. This one is your satellite. It's looking at land and at coastal waters, and with very good specifications. This one is also a very important satellite for biodiversity, looking at both land and water and ocean, but at a coarser resolutions, and this one looks in the atmosphere. I'm not going to spend too much time on the atmosphere. Actually, I will not have a single slide on it. So it's for my presentation will be much more focused on land and on ocean, but of course there are interactions between land and atmosphere and between oceans and atmosphere. The most famous one is ocean acidification. We know this topic, and so you cannot neglect this sort of sentinels. So remember the word sentinel. If you want to know more, you go and visit the ESA booth. I'm sure you've seen it. When you enter in the main hall, it's the one that you see in front of you. And you have all sorts of leaflets about all the missions. Going back now to the subject of these presentations and these environmental conventions, especially the one on biodiversity. I wanted actually to talk about biodiversity starting from these conventions. It's also because at ESA, when we developed major projects, major application projects, we have, it's a big investment. We pay everything. And for us, it's important that actually that we see that there is a potential for a high return on investment. So this is why we decided from the very beginning, about 6-7 years ago, first to learn from in the subjects. I mean, we are engineers, we are scientists, we know what a sensor is, we don't know what biodiversity is, but we can learn about biodiversity. So we started from 92, from the Rio Conventions. I hope that you all know this. If you don't, please spend a bit of time reading these slides. It's started in 92 in Rio with this Earth Summit organized by the United Nations Conference on Environment and Development. And we have the 3 Rio Conventions that were actually adopted a bit later than 92, but they are still called the Rio Conventions. You have your convention, I would say, the one on biodiversity. Then you have the one on climate change, the UNFCCC that you know very well, and the one on to combat desertification. It's important as well to highlight, to stress the fact that all conventions are closely related. Very simple example, climate change is one of the major threats for biodiversity. So you cannot, and there is much more money here than here. So if you really want to voice the problems of biodiversity, go to the conference of climate change and say, yes, but biodiversity. And that's what happened also to them, because climate change has also a big impact of poverty, of food security. And the Convention on Desertification is about food security. So they are all closely linked. And same also, desertification, biodiversity. Okay, I don't have to explain you why there is a link. So what we did in ESA, we decided from more or less 8 years ago now to work with these 3 conventions, what we call the UN conventions, but not only. There is also the Ramsar Convention. Ramsar has its name from a city in Iran when, 40 years ago actually, because we are celebrating the 40 years anniversary of the Ramsar Convention, so it's much older than the Rio Convention. And this was in 71, and it is not in the UN system, so it's an intergovernmental convention on wetlands of international importance. So it's not all wetlands. There are more, let's say, wetlands where, just to give you a simple example, where you have migratory birds stopping to give it wetlands. So it's very important to maintain the ecological character of the wetlands. And we also did some work with the World Heritage Convention. So working with the conventions means also attending the conference of the parties. You probably, I'm always on the wrong one. You probably know these ones, Copenhagen and Cancun on climate change. You might not know these ones because in the media it's difficult to find an article on the Ramsar or on the UNCCD. CBD is getting a bit better. in terms of number of participants, this is 10,000 people. Here we are going down to 3,000, 4,000, 5,000 people. Ramsar, this one we are still in the UN system, so we are still a bit more than 1,000 people, and here, yeah, about the same. Here you have head of states, you might have a few ministers here. Here you don't have any ministers from Europe because we are not affected by land degradation. Just to give you, but money is here, a bit here, and here not much, and that one even less. So you understand sometimes why politics go in some places and not in the other place. But they are all important. They are all very important. So for us, we decided these are all the COP where we attend, and we were showing actually to them what we can do with remote sensing. 4 messages for remote sensing for satellites observation. First message is we have a continuous data acquisition. So with the sort of centers we are using, even if nobody asks for any data, we still acquire. So there's a continuous acquisition of data. We have a long-term data archive. So we have more than now 30, 40 years archive of data. When I say we, I don't mean ESA, I mean all the space agencies. And this is very important because if you want to do some trend analysis, sometimes that's the only way to get information. I'm not saying that you get everything with remote sensing, I'll come to this, but at least you can get a lot. And this allows to do long trend analysis over the 30, 40 years. Somebody can say that 30 years is not enough to do realistic trend analysis on biodiversity. I would say the phenomena is changing quite fast. So for biodiversity, 30 years is a good time frame. We can observe the Earth at different scaling. Many satellites observe this at 1 to 5 kilometer resolution, so they are very coarse resolutions, so it's quite difficult for biodiversity. On the ocean, it can do something, less on land, because land is too much fragmented. You don't see anything at this sort of resolution. Then we move to what we call the moderate resolutions, like the Landsat. You probably know Landsat data that have a 30-meter resolution, and down to very high spatial resolutions in the order of 1 meter spatial resolution. Of course, the higher the resolution, the smaller the footprint. And then last one, which is very important, we can use a different part of the spectrum, of the electromagnetic spectrum. So we can look in the optical part, in the visible part, and the near infrared, but we can also use radar systems. Radar systems are very good to observe through the clouds, of course, because they are not affected by clouds, and at night as well. So it's very important. Well, optics have strong limitations. So if you go in the tropics and where it's always cloudy, no way you can get anything with optical data from space, of course. So the conclusion was that EO technology is a very important tool to support the contracting parties of the convention. Contracting parties are those that have adopted the convention. Because, by the way, you might not know, but the United States is one of the only countries that have not endorsed the United Conventions on Biodiversity. So, let's move now to the next slide. A bit just fundamentals of remote sensing. We all the sensors that we have, I'm talking now at the imagers, so taking an image, because we don't care about the atmosphere. I will only give you a few examples of land applications and ocean applications, and coastal waters as well. So we observe very much in the visible, so that's exactly what you see with your eyes. So from 400 nanometers to 700 nanometers. We observe very much, and this is the reflective part of the spectrum. Here we have, in the infrared part, we have half of it is still reflective, but moving into the infrared. So we have the near infrared, the mid infrared, and we have the thermal infrared, which is emissive. I'll come back on this if, to remind you what emissive and reflective means. These two are passive instruments. So everything is driven by the Earth's radiation. These one are active instruments. They are radar systems. We are working in the microwaves, and we typically use C-band, X-band, C-band, L-band, and now P-band. P-band is a very important wavelengths because it penetrates much more, because you see the wavelengths are increasing here, and the longer the wavelengths, the more you can penetrate into the canopy, so the more you can understand what's in the canopy. If you work only with X-band, you will only see what's happening on the top of the canopy. You can still say a lot, but it's better if you can. There are cases, for example, with wetlands in the Amazon, where with the L-band here, we were able actually to see the water under the trees, just to give you an example. The energy budget of the Earth is very complex. So remote sensing is not easy. It's not that we have the incoming solar radiations, it's reflected by the ground. We know, we want to understand what is the surface characteristic of the ground. We get the reflective solar radiation at the satellite, and it's done. It's a bit more complex because in the radiations, a lot is first reflected by the atmosphere. So what you get at the satellite is a combination of what is reflected by the surface and what is reflected by the atmosphere. But what you want to know is not this, is this. So you have to eliminate the other one. So it's a sort of, we can say, atmospheric contamination. But it's also absorbed by the atmosphere and re-emitted in another, in what we call the long-wave radiations. So here we are more in the visible and the near-infrared, what we call the short-wave radiations. And this part, which is more the emitted part, is in the long-wave radiations, moving from the mid-infrared up to the thermal infrared. So that means two different spectral bands that are observed. Then we have also the problems we have also the latent heat, which cannot really be measured by the systems. And here, the sensible heat. And what else to say? Here, of course, when you are at the surface, one part is reflected and one part is absorbed. What is here important at this level is that for every type of species, of vegetation species, what we want is to understand the spectral behavior for each spectral band of that specific species. You understand? So actually, and this is what we call the spectral signatures. So if you move along the electromagnetic field, you will see that the level of reflections and absorption differs for various reasons. Huh? So this is just highlighting the problem with the atmosphere. The absorption of the atmosphere is given in black here. And you see the visible, the reflective infrared, and the thermal infrared. And you see that there are parts of the spectrum where it's almost impossible to work because the absorption by the atmosphere is really too much. So we have what we call the windows, for example, this one and this one. We call them actually atmospheric windows. So they are really windows to look at the ground. And so this explains why most of the sensors have always more or less the same type of spectral bands. I give you an example because this has not yet been launched. It's an ESA satellite, so I want to show you this. It's called Sentinel-2. And if you compare to other types of satellites, like the Spot series, like the Landsat series, they have a footprint, a swath, which is much larger. So here we have close to 300 kilometers, while the other ones were below 200. 170 for Landsat and actually 60 for Spot. So what does it mean? It means actually one thing is that we cannot observe a certain area in with a single image. And when you want to do some analysis at a given point in time, if you take one acquisition, if you take another acquisition 10 days later, you mosaic them, I mean, you don't represent the state of the vegetation at this given time. So having a larger swath makes that it's much more easier than to do biodiversity analysis. And what we want actually for biodiversity is frequent revisiting time. So having a wide swath allows actually to come back to the same area much more often. High spatial resolutions, I come back to this. Very long durations, it's very important to have continuity of observation. So this is, and this is a high priority for ESA. If we start a mission, even if we have much better mission, technologies improve, continuity is important, because if you want to do an analysis on 30 years, you need this continuity. And we can, with 2 satellites working in a 180 phasing in orbit plane, have a repeat cycle, so that means the time it takes to go again at the same place of 5 days. You have to realize that these satellites, they are in low orbit position. That means the orbit is about 700 kilometers. That means that, and they go around for about 100 minutes. And in the meantime, of course, the Earth is rotating. Yeah? Last one on remote sensing, and now you will start to understand a bit what I'm saying. This is, for example, the Landsat, well, it's actually more the spot bands. Huh? We have the 3 visible bands, and we have the near infrared. This is vegetations. Biodiversity, we look at vegetations mainly. We don't look too much at bare soils, wet water. At least for these explanations. What you see here, this is a typical, what I call a spectrum signatures of the green vegetations. Here, this is due to the photosynthesis. The chlorophyll is very absorbed, what do you call it? Absorbed a lot in the green and especially in the blue, a bit less in the, in the red and in the blue, a bit less in the green, and almost nothing in the near infrared. So you have this form, and this is quite important because if this shifts a bit, depending on the level of photosynthesis, you might actually notice that what you need is actually to know precisely this shape in order to locate, to understand first when does this transition occur, and also to understand the level of this transition. And this is why in the spectral bands of Sentinel-2 we put these bands. You see, these bands are actually located here between 3 and 4. 3 is actually B4 and 4 is actually B8. And these ones, having very small, very narrow spectral bands, allows actually to determine and to characterize the slope. And characterizing the slopes can give you interesting information on the photosynthesis. You see? And actually this is the spectral bands of Sentinel-2 with visible at 10 meter resolution and other ones at 20 meter resolution. And you see the typical 4 bands, so 3 in the visible, 1 in the near infrared. The red edge bands, and these one are SWIR bands, shortwave infrared bands that I use more to look at the water content, which is also very important for biodiversity in order to assess the hydric stress. So very fast on the United Nations Framework Conventions on Climate Change. Well, actually, we've been working in ESA with a lot of organizations. We've been working with the IPCC, we've been working with the Global Climate Observing System, with this international geosphere, biosphere this partnership, but maybe another one. The World Climate Research Program, there's some experiments on ocean data assimilations. They are all important scientific programs that are there to understand the Earth systems. That means the atmosphere, the land, and the ocean, and especially the interactions between them. And one of the outcomes of one of the meetings of the UNFCCC and also some of the report of the IPC is that ESA, together with our other space agencies that are through the group of Earth observations systems, we've provided a response to an implementation plan regarding the observations of what they call essential climate variables. And there are really a lot. So in order to better understand climate, they want to look at a certain number of variables. And for example, ESA, we are doing now the cloud properties, carbon dioxide, greenhouse gases, ozone, aerosol properties, sea surface temperature, sea level rise, sea ice, ocean colors, glaciers, the land cover in general, and the fire disturbance. And this one, what we do actually is a global mapping of all these essential climate variables for 15 years. And this is something, this is for example for sea surface temperatures, and another one for the global sea level rise. This is the last slides on climate change. What I want to stress here, these guys, they were able to identify a certain number of essential climate variables. Why can't we have also a certain number of essential biodiversity variables? And this is feasible, and as you know, there is the IPBES, which has just been created beginning of this year at the UN General Assembly. I don't know what the IPBES will be in the future, but if it does its work, because it's a copy, it's a try to get something very similar to the IPCC. It's an intergovernmental platform with scientists, and we hope that at the end we can get something very similar. A few words now about this global biodiversity outlook. I don't know if some of you had a look at this. This was one of the major reports at the last conference of the parties in Nagoya for the CBD. And it all started in 2002 at the Earth Summit in Johannesburg for the 10 years anniversary of the Rio Convention. And they defined a certain number of targets, the 2010 targets, with main objective was to reverse the loss of biodiversity. So it was decided to have 2010 at the International Year of Biodiversity, and this was released in May 2010, and messages are very clear. Total failure, or let's say collective failure. None of the 2010 targets have been met, so the state of biodiversity is still degrading. But positive, because there are always positive points, even if the message is not so, let's say, it's not really what we expected a few years ago. The UN General Assembly had, during the year, its first General Assembly meeting with a high-level meeting on biodiversity. This never happened before. At Nagoya, they were more realistic. They decided for a new strategic plan for the coming decade with a mission in 2020 and a vision in 2050. And they have these 20-20-20 targets. And they are more realistic. So there is big hope that something can be done. And there is this approval, I think it's in February, but I might be wrong, at the last sessions of the UN General Assembly of this IPBES body. So it's very, very important. Next year, I don't know what will come out of this Rio +20 Earth Summit. It's the 20th anniversary of the Rio Convention, so all will meet in the same place. We don't think that they will reshuffle the conventions, but it's good at least to get a new kick, let's say, to move into the real objectives of the conventions. If you look at what have been the key messages, they said that there is the natural habitats worldwide continue to decline in both extent and integrity. So it's quite important. It's not that, let's say, the areas that are very important for biodiversity reduce in size, but also the content of these areas are also reducing, are also declining. Major threats, and that's where remote sensing can do something, because we can, of course, look at extent and integrity, but we can also look at threats. So habitat loss, of course, is overexploitations of natural resources. I want to say that biofuel is going to be major threats for biodiversity. Climate change, this is why I think both are closely related. Invasive alien species, which is also very closely linked to climate change, but not only, and pollution. But let's say, if you look again at the positive point, more than 170 countries have strategies for biodiversity, have action plans. There is a strong push to develop mechanisms for research, monitoring, and assessment of biodiversity, and that's where we can play a role. And of course, and this is new as well in Nagoya, even if it started a bit before, this economics of biodiversity and ecosystem services. So the idea behind this, I don't know if there was a presentation on this, the idea is that if you want to defend nature, you cannot always claim that nature is important. Just tell that nature has a value. I mean, the message is as simple as this. And then the politicians, they will start listening to you. And so they are still in the early phase, but they have lots of pilot projects on this economics of biodiversities and ecosystems. So what do we do in ESA? Still that I still have a bit of time. We look at what were the focal areas in the diversity 2010 targets in the trends of the biological diversity, sustainable use, the threats, and the integrity. And we identified a certain number of indicators. One is the trends in the extent of certain habitats and ecosystems, the status in some threatened species, the coverage of the protected areas. In terms of sustainable use, of course, to look also at aquaculture and agriculture, which is very important. The trends in invasive alien species, the connectivity and the fragmentations of the ecosystems, and the water quality. So you see that these are global headlines indicators that were used to assess the progress to the 2010 biodiversity targets, and on which we, all space agencies, believe that we can contribute. So there are many. What I want to give you now is a few examples on forest, on the habitat fragmentation, on coastal waters, coral reefs, mangroves, and on wetlands. But be aware that I could have done the same with the dry and subhumid lands, with the Arctic Sea as well, looking at species, looking at invasive alien species, protected areas, and so on. Last two, because I want to insist on these two, biofuels and ocean acidification. This is a new topic, very difficult. Most of the papers have just been published in the last 4 or 5 years. In ESA, we are trying to see if we can do something. We cannot observe acidity, so we have to find a proxy in order to see what is the impact of ocean acidification. For forests, I will start from the red. There's high debate whether red is good or not good. So the red is a decision from the UNFCCC, not from the CBD, on reducing emissions from forestations and forest degradations. But also, and that's the red plus, for conservations and sustainable management of forests, and also the enhancements of forest carbon stocks in these countries. So what the Red Plus is aimed at is encouraging the developing countries to undertake a certain number of activities, which means mainly less forest degradations and less deforestations in order to conserve the carbon stocks. It's carbon oriented, it's climate change, it's not biodiversity. I don't think is listed anywhere in these decisions of the UNFCCC, but if RED Plus is well designed, it can provide a very important benefit for the biodiversity. But there is a strong debate on this, and RED Plus is still being shaped, so there is still place. Just an example of what has been done with Landsat data, so very similar to the Sentinel-2 sensors that I show you. Taking, and this is one of the advantages, we decide, okay, let's look at the Congo basins. We are in 2007, look in the past. So we open the archives. We take an image in the, we took an image in the 90s, in the 2000, in the 2005. And I'm not going here too much into the technology that has been used. We decided to go for a very simple labeling. You see, we didn't put artificial structures. I mean, we were in a place anywhere where they were not present. So we just put cloud burn areas. Is very important, of course, for degradations, land degradations, water. Different types of tree cover, depending on the canopy density, and depending if it's a mosaicing with different type of tree, and other type of land covers, and here we don't mind. What we want to look is at deforestations, and you see here how things has evolved during the last 15 years, with this being other type of land cover, could be agriculture, could be pastures, and this one being, let's say, a forest, which is not anymore a primary forest. So this is probably the most easier type of applications that we can do with remote sensing, but most of the primary forests are in the tropics, they're also the boreal forest. But if you look in the tropics, you have the problems with the cloud coverage. So we have to use other systems, so we cannot use the solar regions. So let's have an active systems, radar systems. And here we were using a C-band SAR, and using, it's a false color composite, where we put, and we took images over 4 years time frame, and putting in the red the temporal variability, the average temperature in green, and the texture, because texture is also very important sometimes to detect SAR textures. It's very important to detect changes. And you see here big changes here, and here in French Guiana. In French Guiana, I can tell you, I have a project called Trap Forest, and it's about, it's about 2 years now that I try to get some images and I don't manage. So we managed to see, you see in red here, the changes. So you can do it with both optical data and with both radar systems. Fragmentation is also very important. This is done in Central America. Again, a very simple legend. You don't need very complex legends to address biodiversity. You can do it, of course. But when you look at such a global scale, you don't need this. And here, what we were looking is the forest fragmentation. So there is lots of ways to define lots of metrics to define the forest fragmentation. This one was very simple. It was just for each pixel to associate to the pixel the patch size to which it belongs. And so you can, and this is very interesting for decision making and for conservation agencies, is really to look at the different fragmentation indexes for this index, but then you can have other type of index as well. Let's move now to coral, mangroves, and seagrasses diversity. I have to be a bit faster here. A few numbers. The coral cover in this zone has fell. I'm talking about the living coral cover from the 80s to 47th of the reef areas, which is quite dramatic. And then they are very sensitive type of species. So they are very sensitive also to the increment of sea surface temperatures. So when we have events like El Niño or La Niña, we can see extensive coral bleaching. This is what happened in the 97, 98. Going to the world mangroves, they are also important for the biodiversity. And you see here the rate of losses in the 90s, in the 80s and 90s and 2000. So it's decreasing, but it's still a loss of mangroves. So what we did here, you might not see it very well. This was a big project done by the USGS in the States using, it's a one-shot project that means in 2000, how many mangroves? And they came up with these numbers, 137,000 square kilometers, and they can drive all sorts of statistics. But it's a one-shot, and they spend a lot of time. They've been using Landsat data archives. They needed to get Landsat data in cloud-free Landsat data. So it's not something that can easily be redone, but at least it gives a reference. And that's the best map of mangroves ever done. This is mangroves present or not present. So it's not a classification of the mangroves. What we've been doing is looking also at some using radar data, because again, the mangroves are mainly the tropical areas, so we have to use radar systems. You can only rely only on land, on optical data. And here we distinguish as well very easy with radar systems the differences between a mangrove and a non-mangrove using a different techniques. And the accuracy, I haven't put the accuracy, but the accuracy is very high. For coral reefs, there are two approaches. One approach is to try really to do a mapping of the habitat of the classes, the habitat classes within the coral reefs. As you see here, where we have a class for seagrasses, for the lagoon, for the reef cress, for the sand, and and actually this is really the reef, and with going into deep water. And this can only be done with very high spatial resolution satellites. So if you want to do a monitoring at a larger scale, you have to work on a different way. What is very interesting is, can we detect coral bleaching? We have to start from the basic reference of the corals that are bleached and of the sand. We applied a sort of radiative transfer model in order to predict what will be the radiance at the level of the sensors, and then we try to see the separability. And we came up with this conclusion, is that coral bleaching is detectable for all coral covers as low as 25%. If we have, this is for complete bleachings, if we have only a partial bleaching events, then of course it starts to be very difficult to detect these events if the coral cover is much lower. So I will go fast now with Ramsar. Ramsar is also very important. We've been working with Ramsar for many years. It's about wetlands. What we try with them is to increase the scientific knowledge to support the management and conservation of the wetlands and to contribute to the performance of the convention. And we've done four type of products with them. The very first one is a land use land cover, but very similar to the I don't know if you know the Corinne land cover maps that we use on land in Europe. And we added the Ramsar wetland classes into this. And so we came up with a very detailed, this was using a Spot 5 data, so quite precise. We came up with a very detailed mapping of the wetland areas. And this is very important for the wetland managers. Another one is to look at the change detection. So you do basically a land a mapping of the habitats at a given time, another one and another time, and you try to see how things have changed. And this is very important in order to do trend analysis and to see how the wetlands have been degraded over the last years. This one is also very important, is how the water cycle is changing within the wetland. The quantity of water is very important, the extent of water. It's very dynamic. That means it's very difficult for us, but we manage actually to map those areas that are always inundated, those that are partially inundated, and those that are always dry. So this is also very important. And the last one is less obvious, is to look at the water quality within a wetland, and mainly the chlorophyll, the suspended matter, and the turbidity, the yellow matter, the mineral part of the turbidity. I'm going fast. A very practical study, 2 slides, 3 slides, not more. This is it okay? Very fast. We had a big catastrophe, you remember, in the Gulf of Mexico, this deep water, horizon oil spill. And we were contacted by the Ocean Foundations, and they asked us to do a special chronology of the oil spill and to look at what has been the environmental impact on land and on sea. So what we've done is that we built some cumulative weekly maps of the areas of the sea that has been impacted by the oil spills, and we've done also some statistics. This is a cumulative map where you see this is where the deep-water horizon was located, and this is the number of weeks where this part of the water has been impacted, or where there was the oil spill. And of course, the more we go away from the deep-water side, the less we have oil spills in terms of number of weeks. You already see the landfall, what you see in black here. And that's quite important because you have the landfall, you know what is the habitat here, and there are lots of wetlands there. And I can tell you that most of the wetlands have been totally damaged in these areas. And this is there is also a very an important place for a needling place for the turtles also in these areas. So it was important to see if this has been impacted. But one of the most interesting applications we've been doing, by the way, the mapping of the oil spill was done by using remote sensing, using radar systems. Here, you see 2 things actually. We come to the bluefin tuna because we talked about this before. And you know that this is a species that might be put, let's say, on the protected species quite soon. There is an fishing practices of this, but the impact of the deep water oil spill has been high, even if Total is always denied, and even the United States denied this. What we did is that with a French scientist, I must say, we overlay the spill from the spills every day from the oil with the spawning habitat index. So that means it's a very complex models where we use different types of input data because we needed sea surface temperatures, we needed sea surface height, we need information about currents, information about waves, and the food. And the food for the larva, because by the way, this is known as being a spawning area for the bluefin tuna. So by knowing the food, that means by knowing where is the chlorophyll, the phytoplankton, and putting this in a model, we can model more with a relevant high accuracy where the bluefin tuna will go in order to reproduce. And when you overlay this with the oil field, you have this sort of animation. And you see the oil spill in gray, and you see the index is actually a probability, because it is probabilistic, of course. It's a probability that the bluefin tuna will go on a given positions in order to spawn. And you see that the impact is quite high, and we have estimated 20% has been hardly affected. So I hope that you agree that remote sensing is a tool for detecting changes in various ways from biodiversity, and I can assure you that ESA will still work closely with the biodiversity.